What is machine learning ML? Machine learning ML is a subset of artificial intelligence, AI, that involves using algorithms and statistical models to enable computers to perform specific tasks without explicit instructions. Instead, it relies on patterns and inference. Essentially, ML systems learn from data to make predictions or decisions without being explicitly programmed to perform the task. Different branches of ML. 1. Supervised learning. Definition: the algorithm learns from labeled data, meaning each training example is paired with an output label. Examples: predicting house prices based on features like size and location, spam email detection. Techniques: regression, predicting continuous values, e.g., linear regression, logistic regression. Classification, predicting discrete labels, e.g., decision trees, support vector machines, neural networks. 2. Unsupervised learning. Definition: the algorithm learns from unlabeled data, identifying patterns and relationships within the data. Examples: customer segmentation in marketing, anomaly detection. Techniques: clustering, grouping similar data points, e.g., k-means, hierarchical clustering. Association, finding relationships between variables, e.g., a priori algorithm. 3. Semi-supervised learning. Definition: a combination of supervised and unsupervised learning where the algorithm is trained on a small amount of labeled data and a large amount of unlabeled data. Example: improving speech recognition systems. Technique: self-training. 4. Reinforcement learning. Definition: the algorithm learns by interacting with an environment to achieve a goal, receiving rewards or penalties based on its actions. Examples: game playing, e.g., AlphaGo; robotics, e.g., robotic control systems. Techniques: Q learning, deep Q networks, DQN. Use cases for different branches of ML. 1. Supervised learning, regression, house price prediction, using features like location, size, and number of bedrooms to predict the price of a house. Stock market prediction, predicting future stock prices based on historical data. Classification, email spam detection, classifying emails as spam or not spam. Medical diagnosis, diagnosing diseases based on patient data, e.g., classifying tumors as benign or malignant. 2. Unsupervised learning, clustering, customer segmentation, grouping customers based on purchasing behavior for targeted marketing. Document clustering, organizing a large set of documents into clusters based on content similarity. Association, market basket analysis, finding associations between products bought together frequently, e.g., milk and bread. Recommendation systems, recommending products to users based on their purchase history. Semi-supervised learning, web content classification, classifying web pages into categories with a small set of labeled pages and a large set of unlabeled pages. Speech recognition, improving the accuracy of speech recognition systems using a small amount of transcribed speech data along with a large amount of unlabeled audio data. 4. Reinforcement learning, game playing, AI agents learning to play games like chess, Go, and video games, e.g., AlphaGo by DeepMind. Robotics, autonomous robots learning to perform tasks such as walking, picking up objects, or assembling products. Self-driving cars, vehicles learning to navigate and make driving decisions in real time. Current developments in ML. 1. Deep learning, a subset of ML involving neural networks with many layers, deep neural networks. Applications: image recognition, natural language processing, autonomous driving. 2. Natural language processing, NLP, understanding and generating human language. Applications: chatbots, language translation, sentiment analysis. 3. Generative adversarial networks, GANs. Two neural networks, generator and discriminator, compete to create realistic synthetic data. Applications: image generation, style transfer, data augmentation. 4. Transfer learning, leveraging pre-trained models on new but related tasks. Applications: improving performance with limited data. 5. Federated learning, training models across decentralized devices while keeping data local. Applications: enhancing privacy in AI applications. Use cases for associated concepts. 1. Deep learning, image recognition, identifying objects, faces, or scenes in images, e.g., Google Photos. Natural language processing, language translation, e.g., Google Translate. Sentiment analysis of texts, chatbots, and virtual assistants, e.g., Amazon Alexa, Apple Siri. 2. Generative adversarial networks, GANs. Image generation, creating realistic images from scratch, e.g., generating faces that don't exist. Data augmentation, generating synthetic data to augment small data sets, improving model performance. 3. Transfer learning, using pre-trained models on large image datasets to improve the diagnosis of diseases from medical scans. Text classification, using pre-trained language models, e.g. BERT, to classify text for sentiment, topic, or spam detection. 4. Federated learning, healthcare, training models on patient data from multiple hospitals without sharing sensitive data. Mobile devices, improving keyboard predictions and personalized recommendations without uploading personal data to servers. Associated concepts. 1. Algorithm. Algorithms are the mathematical instructions that guide how a model learns from data. For example, linear regression finds the best fit line to predict an outcome, while decision trees split data into branches to make decisions. Training data. This is the data set used to train the model. It includes both the input features and the corresponding labels in supervised learning. For example, training data for a spam filter includes emails labeled as spam or not spam. 3. Validation data. This is a subset of the data used to tune model parameters and prevent overfitting. It helps in selecting the best model. 4. Testing data. This is a separate data set used to evaluate the final model's performance. It ensures that the model works well on unseen data. 5. Overfitting. This occurs when a model learns the training data too well, capturing noise and specific patterns that do not generalize to new data. This leads to poor performance on the test data. 6. Underfitting. This happens when a model is too simple to capture the underlying patterns in the data, leading to poor performance on both training and test data. 7. Feature engineering. This involves transforming variables features in the dataset to improve the model's performance. For example, creating new features like average monthly spending from raw transaction data. 8. Model evaluation metrics. These are used to assess the performance of a model. Common metrics include accuracy, the proportion of correct predictions out of all predictions; precision, the proportion of true positive predictions out of all positive predictions made by the model; recall, the proportion of true positive predictions out of all actual positive cases in the data; F1 score, the harmonic mean of precision and recall, providing a balance between the two. Simplified explanation with examples. Imagine you are teaching a computer to recognize different fruits based on their images. Supervised learning, you provide labeled images of apples and oranges. The computer learns to differentiate them based on these labeled examples. Unsupervised learning, you provide unlabeled images of various fruits. The computer groups similar images together, identifying patterns without knowing the labels. Semi-supervised learning, you provide a few labeled images and many unlabeled ones. The computer uses both to improve its learning process. Reinforcement learning, you set up a game where the computer gets points for correctly identifying fruits. It learns to maximize its points through trial and error. In summary, machine learning encompasses various techniques and applications that enable computers to learn from data and make intelligent decisions. Each branch and associated concept has unique use cases, driving advancements in numerous fields and impacting our daily lives.